Thanks for the invitation for giving a talk in this seminar. I will talk on the fourth torsion part of the Brauer group, and this is joint work with Quaternion and Becher. I will start with recalling the definition of the Brauer group. I do believe that most of you is very well familiar with this, but it will help me to fix the notation and the terminology. So let F be a field. Okay, a central simple F algebra is an algebra A over F such that A is simple as a ring. It means the only two-sided ideal that you have are trivial ones. The dimension of A over F is finite, and the center of A is F. The dimension of such an algebra is always square, and if the dimension is n squared, this integer n, we call it the degree of A, and this is the notation I will use. So Wedderburn theorem, this is one of the classical results in the theory. It tells you that if A is a central simple F algebra, then you can find a division algebra unique up to isomorphism and an integer n such that A is isomorphic to n times n matrix algebra over D. Well, and the degree of this division algebra here is called the index of A, and I denote it like this. Wedderburn theorem motivates to define an equivalence relation. Equivalence relation for these algebras, which was first considered by Brauer to study this object. So let's recall. Let A and B be central simple F algebras. We say that A is equivalent to B and denote like this if we can find a division algebra D and some integer n and m such that A is isomorphic to n times n matrix algebra over D and B is isomorphic to m times n matrix algebra over D. Okay, so I can give now the definition. Consider the set of isomorphism classes of central simple algebra over F and quotient by this equivalence relation above. Okay, these are vector spaces over F, right? So you can take the tensor product. The tensor product induces an operation in this set. Usually additive notation is used. I also prefer that. So if I have central simple algebras A and B, okay, I put bracket for saying that I take the class of that algebra in this set. So define the sum of the classes of A and B to be the class of tensor product of these algebras. So this gives you a group structure, and tensor product is commutative, so it gives a abelian group structure on this set, where the natural element is given by the class of whole matrix matrix algebras over F, that is represented by F, and the inverse is given by the inverse of class of A is the class of its opposite algebra. Good. So the order of a class of central simple algebra A in the Brauer group is called exponent of A, and this is how we denote. And it is well known that the Brauer group is actually a torsion abelian group. Indeed, for a central simple F algebra A, the exponent of A divides its index. Now I want to give an important class in the Brauer group, cyclic algebras. I study with the classical definition of the cyclic algebras because I feel more comfortable with that. So I will recall that definition. So let K over F be a cyclic field extension of degree n and an integer. Let sigma be a generator of its Galois group and fix a non-zero element B. Now consider n-dimensional vector space over K with a basis 1j squared up to j to the power n minus 1 and define the following rule. Let j to the power n be equal to B, and let j commute with element of K via this automorphism. That is, let x times j equal to j times sigma x for any element x, for any x in K. Okay, this gives you a ring multiplication on this vector space, and it turns it into a central simple F algebra, and the degree is n. Okay, I will use this notation, commonly used notation for this algebra. I will put into parentheses the ingredient basically that we use: cyclic extension, K over F, a generator of it, its Galois group, and this non-zero element here, element B. Well, the nice thing is that any central simple F algebra of degree n that contain a cyclic field extension of degree n can be described in this simple way. And Okay, this algebra, we call it cyclic algebra. In the case where n is equal to 2, we retrieve the notion of Quaternion algebras. So that is, if K over F is a separable quadratic field extension and sigma is non-trivial automorphism, and okay, be a non-zero element in F, then the cyclic algebra that you construct with this ingredient is called an F Quaternion algebra. In the talk, I will be using the simplified notation for Quaternion algebra in the case where characteristic is not 2. So let me recall that as well. When characteristic is not 2, quadratic extensions are given by taking square root of some element, non-square elements, right? So K will be given as F square root of A for some non-square A in F. And this cyclic algebra here, I will denote by parentheses A and B. Okay, so I already said that Brauer group is a torsion abelian group, is a torsion group. So for an integer n, this is how I will denote the n torsion part of the Brauer group, Brauer subscript n of F. And now I want to give some important result in the theory of central simple algebras related to the torsion part of the Brauer group. First, let me introduce a terminology. This is because it will simplify the formulation for the statements that I'm gonna present. Okay, a class in the Brauer group, which is given by a cyclic algebra of degree dividing n. Today, in this talk, I will call them n symbol. I repeat, a class given by a cyclic algebra of degree dividing n is called n symbol. Okay, so the first result I want to give is Mercury-Suslin, 1982. So they show if F contain a primitive nth root of unity, then n torsion part of the Brauer group is generated by n symbols. Well, they show that n torsion part for such a field is generated by classes of cyclic algebras of degree n. But I give in this formulation because it fits better for the purpose of my talk. So when you have nth root of a primitive nth root of unity, then characteristic of F does not divide n, right? And the analogous result where n is a power of characteristic is also very well known, is actually older, is due to Albert. Following, so let P be a prime number and assume that characteristic is P, an integer, then P to the power E torsion part of the Brauer group is generated by P to the power E symbols. Well, these are positive answers to an old problem posed by Albert, which is actually still open in general. The problem I'm talking about is the following. So for an integer n, we are asking whether n torsion part of the Brauer group is generated by classes of cyclic algebras of degree dividing n. And I already gave you two important cases where the answer is known to be true, right? Answer is known to be yes, right? So the first case is when n is power of the characteristic of F. This was already settled by Albert himself. The answer is yes in this case. The next important case is when F contains a primitive nth root of unity, and this is due to Mercury and Suslin. For prime numbers, where we have a positive answer, are the following prime numbers. So for n equal 2 and 3, the problem has an affirmative answer. When characteristic is n, it is by Albert, and when characteristic is different from n, this is due to Merkuriev. And note that in the case where characteristic is not 3, also when third root of unity is not present, the answer is yes in this case. And the case where n is equal to 5, settled by Elie Masri. So also for the case n equal to 5, the problem has a positive answer. So it seems, so the smallest integer where the problem seems still open is n equal 4. Okay, when characteristic is 2 then Albert result tells you that the fourth torsion path is generated by 4 symbols. And when characteristic is not 2 and square root of -1 is in the base field, then Mercury-Suslin apply. So the remaining case is when characteristic is not 2 and square root of -1 is not present. So it seems that the problem is, in this case, the problem is still open. And the aim of my talk is to provide an affirmative answer to the problem in the case where n is equal to 4, also in this case. Okay, so I want to give the argument, and to do so, I will first work on the p-power torsion part of the Brauer group and make some observation related to the case 2 here, that is when we have suitable primitive roots of unity, and then concentrate my attention to the case 4 torsion part. Okay, so let's start. Let P be a prime number. Well, our argument is based some 2 results that I'm gonna present now, very well-known results. So the first one, let's read this. So let n and m be integer with m smaller than or equal to n, and take a non-zero element b in F. Consider a cyclic field extension L over F, okay, and of degree p to power n, and let sigma be a generator of its Galois group, and take the subfield, cyclic subfield K of this field extension of degree p to power n. Okay, so this is, okay, this is p to power n. So, okay, if you consider the cyclic algebra that you can construct with this cyclic extension L over F and the non-zero element B, if you take the tensor product of this algebra with itself, p to the power n minus m times, then in the Brauer group, you obtain the class given by the cyclic algebra that you can construct with this cyclic subfield K over F. And okay, the sigma is the restriction of sigma on K. Of course, this is a F automorphism of K, but this will be a generator of Galois group of K over F. And so the cyclic algebra generated by K over F and with the same B here. Okay, so this is the first result that I wanted to give. And the second result is about the necessary and sufficient condition for a cyclic field extension to be contained in a larger cyclic extension, but for the fields where you have primitive piece root of unity. So let me recall. Assume that F contains a primitive piece root of unity, zeta, and let E be an integer. Then a cyclic field extension, K over F, of degree p to power E, is contained in a cyclic field extension of degree p to power E plus 1, if and only if zeta, this primitive piece root of unity, is a norm in your cyclic extension K over F. Okay, so now using these 2 results here, we can give a necessary and sufficient condition for a cyclic algebra to lift a cyclic algebra in the Brauer group when we have primitive piece root of unity. Let me state precisely. So assume that F contains a primitive piece root of unity, zeta, and let E be an integer. Take a class, alpha, a p to power E symbol, then the following are equivalent. So alpha is a class of a cyclic algebra of degree p to power E, which has a cyclic subfield of degree p to power E, in which zeta is a norm, okay? And this is equivalent to the fact that alpha is equal to p to power p times beta in the Brauer group for a class beta given by a cyclic algebra of degree p to power E plus 1. Okay, I want to prove this. So let's prove this. 1 implies 2. Okay, so we have alpha is given by, I will directly choose a representation for underlying cyclic algebra. Okay, alpha is given like this. Okay, cyclic extension, cyclic algebra of degree p to power e. So this is sigma p. Let me first write. Okay, so this is a cyclic field extension of degree p to power e. Sigma is a generator of its Galois group, and B is a non-zero element, okay, in your field. But the assumption is that it contains a cyclic subfield where zeta is a norm, okay? Okay, this cyclic subfield I choose such that zeta is a norm in K over F. Okay, so now P to the power E, yes. Now, you see, since zeta is a norm in this cyclic field extension, I can use theorem 2. I wanted to write theorem 2 to find a cyclic field extension of degree p to power e plus 1. Okay, this is cyclic extension of p to power e plus 1 containing k. And okay, I didn't give the proof, but if you prove this theorem, you see that you extend also the automorphism, right? Your automorphism sigma, you can extend to an F automorphism of L sigma prime, I will write, okay, which will be a generator of a Galois group of L over F, such that when you restrict this automorphism on K, you recover the sigma. Okay, so sigma prime, let's write this is sigma. Well, now I consider the following class given by, okay, now I have a cyclic field extension of degree p to power e plus 1. I can construct a cyclic algebra, right? And okay, it's a generator of its Galois group, and I use the same B here. So this will be cyclic. This is a cyclic algebra of degree p to power e plus 1. Okay, now I just compute. Okay, let's compute p times beta. Okay, this is in terms of algebra. This means that you take tensor product of this cyclic algebra with itself p times, right? And here, okay, I use theorem 1. This class is the same as the cyclic algebra that is given by that you construct by cyclic extension K over F and the restriction of sigma prime on K, which is your sigma and B. Well, this is our class that we started. Okay, so these show the implication 1 to 2, and the other implication is even simpler. Okay, let me do this. So 2 implies 1. Okay, alpha is given as p times beta, where beta is a class of cyclic algebra. Okay, given cyclic algebra of, I want to use same letter so that to avoid the confusion. So it's a cyclic algebra of degree p to power e plus 1. Okay, I use L for this cyclic subfield, sigma and B. Okay, and now, yes, now, okay, first let me take the cyclic subfield for E, and then, okay, the restriction of sigma on K. The thing is that, okay, let's first compute this class. Okay, alpha equal to P beta. Using theorem 1, we see that, okay, using theorem 1, we see that this class is given by cyclic extension given by this ingredient here. Okay, but now, okay, so this is, yes, okay, so this is cyclic algebra of degree p to power e. So this is cyclic field extension of degree, so it contains cyclic field extension of degree p to power e, but it is a correct one in the sense, you see, K is contained in this cyclic field extension. So theorem 2 tells you that zeta is a norm in this extension. This is theorem 2. And yes, so this gives you the item 1. Okay. So now let me introduce a terminology motivated by this corollary. So given a p to power e symbol alpha in the Brauer group, we say that alpha has a p-lift if two equivalent conditions from this corollary here hold. Okay, so for the later use, let me already make the following remark. If you have primitive p to power e plus 1 root of unity, then any p to power e symbol has a p-lift. This is because, okay, so okay, this is because, okay, if you denote by, okay, let zeta be primitive p to power e plus 1's root of unity, then zeta to the power p to the power e is a primitive p's root of unity, right? Okay, this is yeah, trivial, but what it means is that if I am given a cyclic field extension of degree p to power e, I can realize this primitive p's root of unity as a norm. So a p to the power e symbol, of course, will have a cyclic subfield, and because of the hypothesis on F, I will be able to see this primitive p's root of unity as a norm, and this tells you that you are satisfying the item 1, and hence you have a p-lift. Okay, so now using this, we can make a simple observation, namely when a p power torsion part is generated by suitable symbols, suitable, I will require to have p-lift, then we can deduce that the next p power torsion part is generated by symbols. Let me write it precisely. So this is what I wanted to, this is what I was telling. Assume that F contains a primitive p's root of unity, zeta, and let E be an integer. Assume that the intersection here, P Brauer F, with p to power e torsion part is generated by p to power e symbols that has a lift. Then p to power e plus 1 torsion part is generated by p to power e plus 1 symbols. Okay, let's see this. Okay, so I want to show that p to the power e plus 1 torsion, p to power e plus 1 torsion part is generated by p to power e plus 1 symbols. So let's take a class alpha in Brauer p e plus 1 f. Okay, then p times alpha is in this intersection, right? So p times alpha is in this intersection here. This is p. P to power e f. Okay, so the hypothesis tells you that p times alpha is given as sums of, okay, let me write, sums of p to the power e symbols, symbols which has a lift, having p lift. Okay, this means that the item 2 of the corollary, this means that for each of these alpha i's are given simply p times beta I. For beta i's are sorry for this, p to the power e plus 1 symbol, right? Okay, now we just make a computation. So p to the power alpha is equal to the sum of these alpha i's, but they are equal to p times beta I. Okay, we are in a group. Oh, sorry. We are in a group. So this is at the same time equal to p times beta i's. And this means that p times alpha minus this sum here is 0 in the Brauer group, right? Okay, so this implies that this class here lies in the p torsion part of the Brauer group. Well, here you have primitive p-th root of unity present, so we can so I will use Merkurjev-Suslin related to the p torsion part. So Merkurjev-Suslin tells you that you can write this class as, okay, beta i's, this is n, as sum of, okay, this is not nice, sum of classes of cyclic algebras of degree p, right? So that is, these are p symbols. P symbols. And this is, okay, the same thing. You can write, this means that we can write alpha as sum of beta i's plus gamma i's, and here beta i's are classes of cyclic algebras of degree dividing p to the power e plus 1. So p to the power e plus 1 symbols, and gamma i's are p symbols. It means that we wrote alpha as sum of p to the power e plus 1 symbols, and this is what we wanted to show, because this applies to any class, of course. So this proves the proposition. Okay, and now we can conclude the following. So let E be an integer and assume that F contains a primitive p to the power e-th root of unity. Then p to the power e torsion part of the Brauer group is generated by p to the power e symbols. Okay, here this is now very this is easy to conclude. The thing is that you have in particular primitive p-th root of unity, and I am again I will use Merkurjev-Suslin result related to p torsion part. So in particular, let me just write Merkurjev-Suslin like this. So Merkurjev-Suslin tells you that Brauer p torsion part is generated, right? Is generated by p symbols. But the remark that we already I already made, since in particular you have p square roots of unity, this tells you that p symbol have a p lift. So each of these generators, whenever you take a generator class of family of generator, they will have a p lift, having p lift, and so you can apply the proposition. Hypothesis of the proposition above is satisfied, and this tells you that p to the power p square torsion part of the Brauer group, p-square torsion part of the Brauer group is generated by p-square symbols. Okay, now you can repeat this argument e minus 1 times, because we have p to power e, its root of unity present, to deduce the statement. Namely, p to power e torsion part is generated by classes of cyclic algebras of degree dividing p to power e. So let me repeat. We use Merkurjev-Suslin result related to p torsion part, and or argument here, proposition, I mean, to deduce the result, but in the version that I present in the talk, to deduce the result related to p to the power e torsion part of the Brauer group. So this was the first remark that I wanted to make, and now I will concentrate on 4 torsion part, and assume from now on that characteristic is not 2. Okay, so our argument here, okay, we rely on some long exact sequence of cohomology groups, 2 of them. I will tell them, but I will write everything in terms of algebras because I'm interested in this. So let's first read the proposition and then discuss. Let A be a central simple F algebra, exponent 2. Then the following are equivalent. So A is equivalent to tensor product of a central simple algebra B with itself, if and only if the cup product of A with -1 is trivial in the third cohomology group of absolute Galois group with coefficient in μ2. Okay, so this equivalence, okay, there will be another equivalence also I will give, but let's concentrate now on this equivalence here. So this equivalence also in terms of algebras has been writing. Let me stress this in the paper, in the article of Tignol, Lieb, and Lam. They present such a result exactly in this form, and let me give the idea. So here, okay, the exact sequence that we are interested in, the parts that we are interested in, let me write it. So H2, second cohomology group of absolute Galois group with coefficient in multiplicative group of separable closure of F. Okay, and the same F. Yes. And here we go to H3 with coefficient in μ2. Okay, so this I'm sure that everybody here is familiar with. This we obtain via squaring map. So this is indeed taking 2 power, and this is the connecting map delta. But okay, I see these. These are for me Brauer group. Okay, and so this is yes, very well known exact sequence. So it's not surprising that delta map has been computed for some classes. So I will write what in the article Lam, Lieb, and Tignol does. So they compute the image of an element. Okay, when you are in the 2 torsion part, they compute that the image is given by taking cup product. Okay, so now basically the proposition is just reading this, reading the exactness in this term here. So if you, okay, for example, for 1 implies 2, basically you start with a class here. This is, as I said, this is taking 2 power, and okay, composition is being exact means in particular the composition is trivial. So this is okay, this is trivial, and if it happens that this is this is in the Brauer two torsion part, as in our case. Then, okay, this, if this is the same class, then this is of course image of A. And as I just said, the delta map for such class is given by taking cup product. So this is the item 2. And okay, this directly gives you the implication 1 implies 2. And on the other hand, if you start with the class of A, and if it is trivial, when if the cup product with -1 is trivial, it means that since it is in the two torsion part, it means that image under this connecting map is trivial, and hence it comes from an element here, meaning that you can find a class B here such that A is given 2 times this class. And this tells you this gives you the implication 2 to 1. Okay, and as I said, this already presented also in these terms in the article I mentioned. Yes, the article that I'm talking about is Quaternion algebras and quartic extension. And okay, this is equivalent at the same time to the following, and this is what we conclude, and using another exact sequence. So it is equivalent at the same time that A is given in the Brauer group as tensor product of Quaternion algebras, SITIs, where SIs are all non-zero sums of 2 squares. Okay, let me give the idea here, really vague. Okay, you are hearing me, right?
Yes.
Okay, just I saw some remark. Sorry. Okay, I continue then. So, and here the part that we are interested from this exact sequence. Let me write it. So here is 2f with coefficient in mu2. So here we are in two torsion part. So yeah, second convergence group of absolute Galois group with coefficient in mu2. Okay, wait, sorry. Here I will discuss the case where -1 is not a square. So let me set k equal to f square root of -1. So here we have k mu2 and h2 f mu2 and h3 f mu2. Okay, so maps, let me give you the maps. So this is taking cup product with -1. This is induced by co-restriction, and this is extending scalar, induced by extending scalar. Again, I am just seeing them as Brauer groups. So this is for me two torsion parts of the Brauer group of K, and this is Brauer 2 of F. Okay, so now if you read item 2, it's mean, okay, you have a class here, right? A has exponent 2, so you are here, and it maps to 0 under this map. Okay, now I will read exactness in this factor here. So let me write, well, A cup product -1 is 0 if and only if, okay, this element comes from here, right? But let me, I will write in terms of algebras directly, if and only if there exists a central simple algebra over K of exponent 2 such that A is equivalent to co-restriction of this algebra here. Okay, now A prime has exponent 2, right? So I use Merkurjev theorem. So this means that it is given as tensor in the Brauer group. It's given as tensor product of Quaternion algebras. But here I will choose a representation that make it easier to work with. So you see, K is a quadratic extension, quadratic field extension. The degree is K is just a quadratic field extension. So for A prime here, I can choose such a representation. Okay, this is good. Okay, I can choose such a representation. Xi T, I put T, so let me use T now. K, these are K quaternion algebras. Okay, I can choose them in a way. Okay, these Xi's are in K and Ti's are in F. This is because K is just degree 2 extension over 2 over F. So now, okay, taking co-restriction of A prime, I just need to compute the co-restriction of these quaternion algebras, and yeah, projection formula. We can use projection formula. Then, okay, A is, well, co-restriction of A prime, and this is, okay, taking co-restriction of these quaternion algebras is just norm of these Xi's, right? And Ti. This is projection formula. Okay, now I set Si equal to this norm of Xi. But okay, Xi's are in K in this field. The norm of an element in this field extension here is sums of 2 square. So Si is non-zero, sums of 2 square in F prime. And okay, I just rewrite. This is just putting Si here. And this is what I wanted. F quaternion algebras. Okay, so this gives you the proposition. Well, okay, now you see the equivalent. Actually, I'm interested in the equivalence between 1 and 3. So let me tell you what it means in terms of today's terminology. So it is actually means that we have this intersection here, 2 Brauer F with fourth torsion part is generated by classes of quaternion algebras where -1 is reduced norm. Okay, so sorry. So this intersection here means that you are having classes A satisfying this item 1, right? And proposition tells you that this class of A's can be given as tensor product of quaternion algebras, where quaternion algebras are given as like SITIs, where SIs are sums of 2 square. So the only thing to be remarked to remark here is that if you have a quadratic extension, okay, quadratic field extension, then -1 is a norm in this quadratic field extension, if and only if K is given by taking square root of S for some non-zero sums of 2 square. Okay, so this gives you the corollary here. So, and it's mean, okay, the terminology that I introduced today, this means that this intersection is generated by 2 symbols, right? 2 symbols having a p-lift, a 2-lift. Hence, we can use our proposition to deduce that fourth torsion part of the Brauer group is generated by classes of cyclic algebras of degree 2 and 4. Okay.
So this remark about the sorry, this remark about the -1 being a sum of 2 squares.
Yes.
Is already used in the proof of the proposition, right? You need it there as well.
-1 being a norm. Yes. Wait, can you just repeat? I didn't.
you use this remark in the proof of the corollary, but you also need it in the proof of the proposition for one of the directions there. That's my question.
-1 being a norm in.
I mean, don't you need
No.
it to prove that 3 implies 2?
Mm-hmm. Yes. Okay. As I being sums of 2 square is mean that it's a norm in this field extension.
Yeah, sorry, I just wanted to clarify. Thank you.
Okay, let me conclude, and then we can come back as well if you want. So this shows you that fourth torsion part is generated by 4 symbols, and okay, I wanted to say that okay, the way that I gave the argument is maybe not that visible, but if we use the argument in a bit of a careful way, that is, if we keep track of the cyclic algebras that we lived, the number of them, it also yields bounds on the index of these algebras, and in the case of the theorem, it means that we obtain bounds on the index of exponent-4 algebras. Let me conclude my talk by providing these bounds. So all bounds we obtain in terms of u-invariant. So let me recall first. Okay, the u-invariant of F is defined. Recall that the u-invariant of F is defined as the supremum of dimension of anisotropic torsion quadratic form over F. So actually, we obtain bounds for exponent-4 algebras defined over non-real fields. So recall that a field is non-real if -1 is sums of squares. So assume that -1 is sums of square in F, and take a central simple F algebra A such that exponent is at most 4. Then the index of A is bounded by 2 to the power 3 times u-invariant of F over 2 minus 1. Okay, so yes, this was all what I wanted to tell. Thank you, and we can proceed with questions.
Are there any questions?
Okay, so if nobody starts, I have one. So, so what about odd primes?
Please go ahead.
Yes.
Odd
what
primes.
about odd primes? Yes. Do you have expectations?
Yes, actually,
Philippe, we can't hear you.
This is me actually. Yeah, this is actually what I want to do next, because you see in our argument, everything is given when you have piece root of unity, and the thing is that I use Merkurjev result and then our argument. So when we have piece root of unity, okay, no, sorry, this was yes, when we have piece roots of unity, then Brauer group is I can use. I would try. I haven't tried yet, but I would try to see if this extend. So P torsion part is generated by symbol algebras, right? of degree p, and these are very similar to Quaternion algebras. And for example, the first step, I can try to see already if it extends. So actually, I would expect that it is more possible for p square than 2 powers, but I haven't find time yet to do. But I would try first to do a similar way.
Okay, thank you.
Thank you.
So nobody is asking questions. So is there a paper? I mean, a preprint?
For this, not yet. It is included in my thesis, and soon, hopefully, I will try, but not yet.
Okay, thank you. Zinovi? Ah oui. Bon. So please, Kirill, you please.
Okay. Is any other question? Any other question? Okay, then if not, let's thank our speaker.
Okay.
And we will resume.